Good afternoon. I'm Hunter Enders. I'm working on catalyzing engineering innovation with generative AI with Dr. Pete Ludovis of the Engineering Entrepreneurship Program here at the University of Alabama. We're looking to take an improvisation workshop that explores design idea space through a Monte Carlo type model developed by Dr. Ludovis and coworkers and replace that with AI technology. Humorous improvisation is chosen as the driving force for exploring idea space here because of its inherent similarity to innovation. We begin by asking, what is humor? And two of the most commonly accepted definitions given by Raskin, Dennett, and Hurley basically say the same thing, that humor is our response to two very different ideas that are ironically similar in some way. Luckily, innovation works the same way, allowing the application of an idea for the potential solution that is creative because it would normally not be appropriate, but is appropriate in some non-obvious way. This is illustrated in the next slide. The incongruity requires a shift in thinking, something that the creativity innovator DeBano calls lateral thinking, to something that does not seem appropriate. For example, we have a joke here. To most people, mayonnaise and olives would not serve as a good substitute for chocolate chip ice cream. But if the similarity here is that if you look closely, or if you don't look closely, they look very similar, right? You might get them mistaken. Similarly, it would be comical to replace all the people working in stock exchange with computers. But that's exactly what happened and was the basis for the NASDAQ stock exchange, which is common in almost every stocks and commodities exchange. You'll see the innovation figure on the right was actually used in an ASEE paper by Dr. Ludovis and his colleagues, and we used a joke from the show The Office. Our goal is to use a Monte Carlo type model to sample idea space. These models use the same random variations observed in gambling to converge on various solutions. Here is the simplest variation of MC models, which can be used to calculate pi from the relative areas of a square and a circle. We begin by defining the statistical search system based again on a square and a circle. We generate random states, in this case a point inside the square, and then we count, is it inside the circle? If it is, we count it, and we do this over and over again until we converge on a solution. This is how Monte Carlo models work. Dr. Ludovis also uses these kinds of models to explore equilibrium chemical states, and we propose a Monte Carlo model that explores idea space for possible engineering design solutions. As before, we define our system, which uses ideas randomly generated by an improvisation skit, which is just two or more people acting out a skit. And we compare them to a design challenge to see if this comparison generates some new creative potential design idea. If it does not, we look for more random ideas from the improv session. But if it does, then we hold on to these ideas and we consider them later. In a previous chemical engineering senior design class, the Exide Battery Company was looking to redesign a reactor that sprayed sulfuric acid on lead oxide particles to create a paste that served as the electrolyte in lead acid car batteries. They wanted to increase the size of the reactor, but the problem was they couldn't reach all of the particles, and then when they tried moving the sprayers in the middle of the reactor, the sprayers would clog up. So this was a perfect opportunity here. A joke was brought up in an improv session about a bear farting in the woods. And a participant in the improv session thought of a quote from the movie The Bucket List, where Jack Nicholson says, "At my age, you should never trust a fart." Now, further consideration of this idea, while it may have been a joke, ended up serving well. They thought of, what if we change the phase of the sulfuric acid to gaseous SO3, exposed to lead oxide particles covered in water, to produce acid from water reacting with the gas. And this worked. The gas completely filled the reactor, so there was no problem reaching all the particles. And Exide loved the idea. They chose it as the best idea for this reactor design. In practice, the improv occurs where everyone writes in two lists. On the left, you have random ideas from the improvisation, and then on the right, your second list, you have potential design ideas inspired by those random funny improv ideas. You'll notice in the picture here, this is from an ASEE meeting with Dr. Ludovis and his colleagues, that on the left you have some random ideas, and in some instances there were no design ideas that stemmed from it, as you can notice from the blank spaces on the right. Applying the Monte Carlo model to our research, we turn to the concept of idea distance, which basically says an idea might be similar or it might not be. Idea distance presents a challenge. Dissimilar ideas are harder to put together, harder to make something practical out of. Sometimes we'll have ideas that overlap clearly. Sometimes ideas seemingly have no overlap. And even yet, we have ideas that need intermediate steps to be linked. Machine learning models and AI software currently often struggle with distant ideas that don't seem to be very, very similar. But we need to gauge similarity between ideas to see if there is a way we can get it to suggest practical applications. To do this, we were looking for a similarity metric. We used ChatGPT version 4 output, and we want to quantify that similarity that ChatGPT gives us. We have some factors that we've considered in an algorithm we created. These include sentiment analysis. We used a tool provided by MonkeyLearn to see, does ChatGPT give a certain connotation to the way it describes similarity of two ideas? We looked at the keyword count for keywords like similar or different. We also looked at meaningful modifiers, so think of adjectives, adverbs, words like quite or primary. We also note that GPT is very verbose. It sometimes likes to give you things just for the sake of giving you things. So we did consider the number of similarities, but we didn't really think that word count was all that meaningful. Notice in the example here, we asked ChatGPT for similarity between two ideas, cabinet and bowling alley, that seem to have very little in common. GPT notes here that this is mostly a creative exercise to try and compare these two things. It doesn't want to provide any sort of practical application. It goes and it defaults to the human imagination. We have generated an algorithm to get an actual similarity metric, to get numbers that we can look at. We'd like to score this from 0 to 100, adding points based on the aforementioned factors from the previous slide. As you can see from this formula, there are a lot of variables that we have to take into consideration, and we definitely welcome any suggestions or recommendations for refinement for our algorithm. We want to get scores that are more agreeable and we think provide the most accurate look at similarity. Here we have some results from testing 11 random idea pairs. This chart shows that some are very similar. They had scores close to 100. Others had barely any similarity to each other or moderate similarity, as noted by the lower scores. But all in all, you see from this chart, it's really hard to consistently predict the similarity you'll get from our algorithm. And the resulting similarity score for any given pair of ideas might be quite surprising. We definitely think any user could disagree with that. And we are open to tweaking things, and we want to make this the best we can, because if we have the most reliable similarity metric, we believe we can get the most reliable connections and practical applications. We have some key takeaways from our research, first being that similarities are largely subjective. Our algorithm aims to provide a more objective metric, but there is room for debate and improvement. Second is that AI often struggles. It doesn't often provide meaningful applications for comparison. Instead, it looks at comparisons as a means of creative exercise rather than for practical purposes. So we can't rely on it as a crutch or a pure alternative to human thought. Third, we note that the human mind is brilliant. It's capable of limitless imagination, and we think with AI tools as an aid rather than a substitute for human thought, innovation can be sparked at any given moment. Our overarching objective is to provide an AI alternative to innovation improvisation workshops, as we noted earlier. We want to provide better results with bonuses of speed, convenience, and ease of access. To be successful, we'll continue testing AI software to determine if certain prompts give certain better results, or if there's a competitor model out there that will give better results. We want to refine our algorithm to give the best similarity metric. Also, we focused a lot here on similarity, noting again that AI struggles to give you those practical applications. We are hoping in the future that as AI improves, we can focus more on using the AI itself to come up with applications rather than as a help in brainstorming oneself. And finally, once we can get the AI to suggest practical applications, we like to develop an app to be used here at the University of Alabama, then at other institutions, and hopefully even by the general public. Thank you. Are there any questions?
So is your research uniquely useful to engineering, or do you see any uses it may have in other professions as well?
We definitely focused a lot on engineering here, but we think that it could be used in almost any profession for almost any purpose. I look at myself as someone who comes from a computer engineering background and has some business experience, and Dr. Ludovis with his chemical engineering background and his work in entrepreneurship. We both looked at this as a way of how can we make something new engineering-wise, but also how can we help a business owner, come up with creative ideas for maybe a way to gain an edge So we definitely think it could be useful for engineering, but also for other professions. And we welcome any advancements and uses by other professions.
So as like a more general thing, like do you think users need to practice or like use AI tools often to like get the best results?
Yes, when a user uses the tool enough, they can kind of get a sense for what prompt do I give the AI that will result in the best results. So when you use it enough, you start to get a feel of, if I ask it this, is it really going to give me the output I want? That was something I've learned over the course of this semester. And also there are some AI models out there that will learn over time from the responses you give. So there's no guarantee that practice will give you the results you want, but it is likely that repeated use will yield greater levels of success.
So in your similarity analysis, you mentioned some very specific tooling, so ChatGPT-4 and a specific sentiment analysis tool. Those no doubt are going to evolve and change. So how do you plan to incorporate those changes and perhaps even some whole new paradigm shift? How will you bring that into your similarity analysis for the future?
We definitely see a lot of the advancements and improvements in that field as good things. We believe that it will only make our tool and our research more effective, make them better and more usable. We do realize that there are sometimes updates that could limit hardware or people who can use it, because a lot of this stuff is cutting edge. But we do believe that as there are improvements made, that it will produce better results and hopefully better practicality and real-life connections.